right, thank you. And a very special thank you for hanging in there towards the end of the day. It's not cool in here, so I appreciate the investment in time that you're making in this discussion. Hopefully we'll make it very worthwhile for you. So my name is Scott Soutter. I'm a product manager within IBM working in the applied artificial intelligence space. Now, I'll qualify that and say I'm actually not in the part of IBM that gets a TV commercial when they talk about artificial intelligence. I'm in a group within IBM that has come out of our systems organization in partnership with IBM's research group. And our focus has been on applied artificial intelligence by building a better deep learning training platform. And we've been doing that now for a couple of years. So I'll talk a little bit about what Power AI is. I will be very light on the product pitch part of this and instead focus on why we made some of the decisions that we've made in developing our platform and the impact that that has on you as a data scientist and a developer of new AI applications. And then I'll really want to focus on what I see as sort of three big trends that are happening right now in particularly around deep learning development, but can also be generalized a little bit more towards applied artificial intelligence. And time permitting, I'll show a video, which is always a lot of fun, less risky than an online demo, typically. And then hopefully leave plenty of time afterward for questions and answers. So the three areas that I'll want to hit after our intro really will be around things like large model support, distributed training, and some of the impact that that has on application and data science practitioners, and then really on making the room a little bit bigger. I think we're at an interesting place right now in data science, and particularly around building new models, and it is still just a little bit too rough. Right? The tools need some more polish in order to be more broadly available. And so I'll talk a little bit about our goals there as an organization and how I see this fitting into some of the larger trends within the industry. So to get started, if you haven't seen 5 versions of this chart already today, I will be very surprised. But the general theme holds. You know, we're being buried by data, and without having systems that allow us to bring that under control, without getting us to a place where we can really wrangle that data and understand what is happening within it, we're suffering from this case of enterprise amnesia, where the amount of available data dramatically outstrips our system's ability to contain it and help us analyze it. And it's not getting any better. Right? The more instrumentation out there, the more that we foster this environment where data growth becomes an exponential function, the harder it gets, unless we really dig deep for help. And that is where machine learning and artificial intelligence in the concept of deep learning start to give us the tools. Because fundamentally, these are built around the idea that they can help us process and develop an inference capability to see those subtle patterns within the data that give us value. And our goal as we try to build out our application is to raise the line a little bit on what is understood data versus what is available data. And I know we're never going to hit it all, right? Nor do we want to. Some of this data is truly noise in the background, but we have to raise the line a little bit higher because we are, in fact, losing the ability to find some nuggets of gold, some intelligence in the stream of data that we have today. So enough about the hyperbole section. We built a platform to help data science teams build better applied artificial intelligence. And we're doing it in a way that's quite a bit different than what you see out there today with other services. We treat this as a problem where we have to co-design both the hardware and the software. We've seen a massive change in computing with the rise of accelerators as being so central to the process of driving new AI models. In fact, I believe we would not be where we are today if we hadn't seen both the broad adoption of accelerators, particularly GPUs from NVIDIA, and the fantastic software toolkit that they've built around this in the form of CUDA, and the simplification that that has brought to developing massively parallel applications. So GPUs are extremely cool. Actually, they run really hot. So we try to keep it cool with a lot of air. But they also are very purpose-built. If you can get the data through the system, they do very well. If you can't get the data through the system, if you can't get to the data to the GPU, they starve. You're wasting time, you're wasting money, you're sub-optimizing the system. So within our co-design of hardware and software, we really focus on building an extremely high bandwidth system that gets the data in and out of the GPU at a rate that is far beyond what is available anywhere else. We effectively promote the GPU to the same status, capability, and level in the system as the CPU. And that's very different. And it recognizes this new hardware compute model. We give the GPU the ability to map all of the system memory available in there. I'll talk about that a little bit later in the context of large model support. And I believe that this is the type of design that we will start to see more and more prevalent out there in the industry as more system designers, more folks see the benefit of this. So we're not doing it in a vacuum. IBM has done something in the past 5 years that was brand new for us. We went and we open sourced our hardware design, we open sourced our software designs. And we built a consortium of individuals out there to work together, starting with improving I/O within the system, but also really focusing on programming simplification. And that gave us a great head start in moving into the world of deep learning. So let's talk a little bit about what we have built here. In embracing the open source world, we have simplified the process of bringing the most common deep learning frameworks to organizations bringing deep learning into production. Our focus here has been on hardening the software, making it more accessible to run within systems environments where there are security considerations, where there are data bandwidth considerations. We've also focused on simplifying the deployment of the software. How many folks out there have built TensorFlow from the ground up? Started with open source. How was it? Yeah, painful. Painful is a word. When we did it for the first time, it took us 6 weeks as a development team. Part of that was growing pains as we learned a little bit about the environment. But part of that was the fact that it took us 100 software packages to build the build tool, Bazel, and then another whole handful of them to build the application itself from there. So we took a look at that, and we realized that was not very scalable. That was not going to be very good for an organization that wanted to compute at scale and wanted to be able to rapidly deploy and then update systems, because very active product. It changes about every 4 weeks, right? So even keeping up with that build process is a challenge. So within Power AI, what we've done is we've built an integrated, supported platform that you deliver as a single binary. You can get it as binary software that runs on bare metal. We're bringing it to Dockerized containers. We're trying to get it to the point where it takes you 4 commands and about 30 minutes to do the installation and deployment. If you start at the beginning of when I started talking, you should be done by the time we get to Q&A. But that's really not enough, right? When we get to that point, you have a platform, but it's still too hard to use. And so our focus around there is really embracing and extending the capability of TensorFlow. We started by simplifying the process of distributing software. We treated it like a high-performance computing problem, where you could take the core creativity and functionality within the applications and very simply deploy them across large clusters. When we talk about large clusters, that can mean scaling from a single 4 GPU machine up to 256 4 GPU machines, or as sort of a spoiler, what Uber is trying to do with Oak Ridge National Laboratories, where they're going to scale to 27,000 GPUs. And we're going to do so in a way that makes it very efficient. Because if you're going to buy all those GPUs, if you're going to deploy them, if you're going to run power to them, then by all means, let's get everything we possibly can out of that performance infrastructure. The second thing we focused on in terms of optimizing the performance was improving the way that you can develop by expanding the space of memory that you can operate in. One of the common things we heard as we went out and talked to data scientist teams and developers out there was that the amount of space that you had to operate in was just too small. When you look at instances where you have to take model logic and distribute that, including all the layers within your network, all the matrices within the layers themselves, plus the batch data, when you started to operate against that, it got pretty hard to fit inside of 16 gigabytes. It'll still be hard to fit inside of 32 gigabytes in a month when we start getting bigger GPUs. So our focus there has been really on giving them more room. And that's the story about the work that we've done with something called large model support. And I'll talk about how we've achieved this, and then I'll talk about two other examples of something happening in the industry right now where we're seeing others attack this problem. And we like this because we really see the value in having that more and more creativity against this space. So as I mentioned kind of in the warm-up there, traditionally, limited GPU memory forces you to make trade-offs, typically in either the complexity of the model, the size of the data, either the size of the batch that you're working with, or even the size of the individual data elements. And there's a couple of reasons for that. Number one, it's very expensive to go across this resource here. If you think about a traditional system design where you have GPUs connected through a PCIe bridge, you have a limitation there. You can move data across that bridge at about 16 gigabytes per second, 1.6. And what you can see in our design is we've tried to remove that as a barrier, just about 9 times faster in terms of moving the data between the GPU and the CPU, using technology that we brought in from NVIDIA, one of our partners in the Open Power Consortium, using their NVLink connection to not only connect GPUs to GPUs for better peer-to-peer computing, but connecting them directly to CPUs. It gives us a much faster data path across between CPU memory and GPU memory, which in and of itself is great. That'll get you about 40% improvement in overall training performance. But it enables something that we think is even more powerful. And that is the large model support technology, which we have started to open source into the deep learning community. What large model support allows you to do is to treat all of the memory on your system as a single resource. You can map memory from the GPU through the CPU through other GPUs in one coherent block. So why does that matter in the context of this? What it allows us to do is to load the entire model inside of system memory. We now treat that 16 or 32 gigabyte space down there on the GPU, that very fast, very wonderful HBM2 memory, as a place that you store each individual layer within the network. And we can cache those layers in and out of system memory and perform the reconciliation there. So the effect is that all of a sudden you can, not quite exponentially, but getting awfully close to it, increase the size of your models. And that means no more trade-offs in layer complexity, much larger images, where we can do things like take in native HD video versus having to bust everything down to a tile in order to interpret it during a training workload. Much higher resolution images. Being able to look at a single MRI, which is a gigascale image, and identify an area of interest there. Or if you're working with non-image data, do things like the very complex and large matrix multiplication exercises that you do typically when working with large character or numerical data sets. Very powerful. Turns out it also is a little bit faster. We didn't anticipate this. We thought that as we traded off between HBM memory to DDR memory, we would slow down, which we do. But by virtue of the fact that we're dragging more data through the system concurrently, we're actually able to reduce training time. And we see this as a great virtue. We want this out there. We've started open sourcing this last year. We put it into the Chainer framework by Preferred Networks. We've already built it into Caffe, and you'll see it coming in TensorFlow this June as a technology preview. And then we're going to spin it out there to as many frameworks as we'll take it. We were glad to see that we're also not alone in approaching this problem. And we have spoken with Alibaba about the work that they've done, which is a derivative of some of the functionalities we brought out with our large model support. In fact, they quoted our paper in the way that they described what they have done. We've also seen this start to become popular through the OpenAI Foundation and some of the work that they've done with gradient checkpointing. In terms of capability, what these different organizations have brought in, Alibaba has actually used this as a way to lighten the load on GPU memory so they could potentially run more concurrent workloads on a single set of resources. And they look at that as having a slight performance improvement. They saw about 10% performance improvement in the work that they'd done. OpenAI is straight up just building larger models, much in the same way that we have done with our large model support. And their goal has been building a model that's about 10 to 100x larger than was previously available. And then we were very excited that the Chainer folks in Preferred Networks just wanted to work directly with us to help take what we'd done and be our first open source partner there and bring it out to their community. But what's the use of having a very, very large model if you're not able to get anything done with it? Deep learning training and machine learning training is still a very, very iterative process, and those iterations are long, and they're very expensive computationally, and they're a significant investment in time. So what we've tried to do with the work that we've done in this space is to decrease those iterations, make this look a lot more like interactive computing rather than the very, very long-running batches that you typically see in a deep learning training exercise. And we've done that with what we call our distributed deep learning technology. Distributed deep learning is inspired by what we've done in HPC in that it uses a very strong high-performance computing set of libraries that sit underneath deep learning frameworks. We modify the code slightly for where we're using native TensorFlow and Caffe, and over time, other frameworks such as PyTorch, which is a strong candidate for this. We not only put a better communication layer under there using something called MPI, which has very low latency and very high throughput, but we also provide a very novel way of distributing the data across nodes and the model logic across nodes. We distribute parameters as part of this. And our design point here is make it simple. We want to give anybody who has the ability to develop a model that will cross and span 2 GPUs the ability to span it to 2,000 GPUs and do so in a way with very, very limited modification. Now, this is something that's fairly purpose-built Today, when we build this out, it runs on a bare metal infrastructure, so you have a deep learning cluster and you're going to run that thing flat out like an F1 race car. But we hope that we'll be able to extend this to a more cloud-friendly, containerized environment over time. So watch this space. The specifications and the work that we've done show pretty good efficiency. When we built this out, we actually scaled from 4 to 256 GPUs with a loss of about 5% of ideal efficiency. So again, if you're going to buy 256 GPUs, at least use 240 something of them. And we've done so in a way that starts to bring all of this training time, which represents one of our servers across 16 days, down to something that's under a day. And if you do some of the work, like you've seen with the folks at Uber, where they're trying to take some very similar technologies with their Horovod distribution capability, which can run with DDL, or it can run with Nickel 2, NVIDIA's GPU distribution library, you're starting to see the same level of efficiency and scaling. So we think that this has legs. Now, to you, what this means is more time spent on modifying and adjusting and getting value out of tuning your model, not so much waiting. And we think that that will start to stimulate more creativity and capability around model design. Today, this is something that we offer largely in our on-premise environments, but it's something that will be coming to our cloud soon as well. We're not alone in this. We see some other approaches to address this problem that look at it not so much from an extreme scalability standpoint, but from an efficiency standpoint. Being able to change the makeup of your cluster as your training job evolves. Do things like kick off a training job that may require 32 GPUs, and then as that reaches more of the end of the training cycle, pull those resources out. Do those in an elastic way that will allow you to then deploy them onto another project. A lot of this is built with the idea of a shared services GPU cluster, but we see this as a major emerging trend in the industry, and it is something that we really embrace as we start to look at how organizations and IT departments consider the challenges of maintaining that shared services, multi-server GPU environment that's necessary to support both development and production inside of deep learning. We're not seeing this limited to deep learning either. We're actually seeing some interesting evolution in what's happening in the machine learning space. We saw through some of the works that had been done on XGBoost, some substantial increase in performance around machine learning capability, and we sort of took up that gauntlet as a way that we can look at how we can better accelerate very, very common machine learning functions, which are where we see a lot of our customers in industry today spending their time. We announced about 4 weeks ago this capability in the form of something called SnapML, which is a separate library that can plug into Python, can plug into Scikit, can plug into Spark, or eventually TensorFlow, and accelerate both sparse matrix problems and common machine learning work in things like logistic regression, linear regression, and support vector machines. It's another of one of those gee whiz sort of numbers that we've seen. Well, what this does is it showcases the promises of taking something that have otherwise been difficult to accelerate because of that problem of bringing that sparse matrix calculation into the GPU, into something that makes machine learning now far more interactive. And our experience with this was in taking a workload that ran across 89 systems on the Google Cloud, with 70 minutes running purely in CPU mode, and bringing it down to about 1.5 minutes running across 16 GPUs and 4 servers. So if you guys are interested, this is technology that we're bringing out as a tech preview in June, and we're looking for folks who want to give it a test drive. So get in touch with me. We'd love to share what we've done there. So last sort of topic area. All of what I've talked about so far is tremendously exciting, but the tools are still too difficult to use. They're out of reach of large portions of the development team within an organization. The software is pretty fragile, and so it doesn't always scale very well. And the tooling is esoteric, right? It's difficult to understand unless you come at it from the perspective of having a good data science background. And what we want to do is help expand this community into a larger group. We kind of see all these folks when we look at our development process as being integral to building a good applied artificial intelligence environment. And so while a lot of the focus to date has been on making you guys very productive, and we're really happy to do that, we want to expand the room a little bit more. So you can get help from folks like data engineering teams who understand how and where data sits within an organization. So we can get active participation in the process of developing a new model from the business analyst, that proxy for the head of the organization who knows what a good outcome is. We want those people deep into the process of building a new model. And then we want to simplify it so that DevOps, so that application developers can very, very quickly include this capability in the other business logic that they work with. So to get there, we started to build tools like this. And I'm going to show a brief demo of something called Power AI Vision, and then we can close to some questions. So Power AI Vision is a very simplified development environment that is aimed at creating computer vision applications. One of the things that are now really enabled by bringing deep learning into the organization. Our design point here is point and click. We would like this to be something that business analyst, that proxy for the organization's leader, to be able to do and be relatively self-propelled. If you saw the driverless AI talk earlier today from H2O, very similar goals, sort of make AI available to everyone and do so in a way that provides a great deal of simplification. So what we're going to show here today is us actually build a AI application, and we're going to build it in a way that uses artificial intelligence to help label data, one of those awful tasks that we all go through when we're using a new data set that hasn't been very well instrumented. So in this case, we've taken some drone video of one of our development parking lots, and we are using this tool to pull out frames from a very small video, and we're going to box up areas of interest. We're going to identify what a car or a person looks like. And we'll do that in fairly low order. This is not a big data training set. We're going to have 17 tagged images by the time that we're done. But we're going to invest about 2 minutes into this labeling process. Then we're going to turn around and we're going to actually export that, and we're going to create a new object detection AI using our Power AI Vision tool that will go through and label data in a much larger data set, something that we can then start to use to train a model with a greater and acceptable level of precision. So what you can see here is what that training looks like. Not terribly exciting, not terribly converging either. But what we're able to do with that fairly weak model is now export it. And we could either export it to use internally through a RESTful API, or we could use it for internal use, which is what we're going to do today. So in addition to our small data set, we've got a moderately larger data set that we're going to bring into AI Vision And we're going to sick this very small model against that. And what you'll see here is we'll set it up as an auto labeling function, and we'll ask that it samples about every second and creates labeled areas of interest. So, drum roll please, our very excitingly named data set called car person. And what you'll see is it tags itself relatively quickly. We'll get to about 200 tags. And then we'll go back through and we'll audit it. And what you'll start to see is, A, the model was a little weak, so it didn't recognize areas of overlap where you had two cars sitting next to each other. But fundamentally, not too bad. We've gone from 0 tags in a novel data set that we've never touched before into something that, in about a minute, we'll export and train to our second deep learning model, which can actually be used for labeling and recognition at a higher scale and a greater resolution. So, neat. Why does it matter? None of what you saw here required somebody to crawl into the complexities of developing tagged data sets, writing XML, or training a model. We've sort of obscured that by simplifying it through a point-and-click interface, and we're trying to bring this into the realm of capability for your subject matter expert, for your head of security, for your head of manufacturing quality. You can go look at a silicon disk and say, that's the thing we're trying to identify. That's the area of interest that says we need to flag this. This is what our inference model needs to be. And that is kind of why we're doing this with Power AI. We want to bring those folks into the process, into the transaction of creating a new deep learning application. We also want to help offload you, get you some help so that you can speed up the process of labeling your data, speed up rapid prototyping, get more models out there faster, make applied artificial intelligence something that's more broadly available. And that, I think, is getting pretty close to the end here. So we have resources available for help. We invite you absolutely to take a look at our Power AI developer webpage, where we run through a lot of what I've talked about today in more detail. We have white papers, we have developer journeys, we have the ability to sign up and get cloud access to the system that we run on the IBM cloud with one of our accelerated power systems. And there's also a developer journey that's there, so you can practice, so you can kind of get a feel for what it means to use the large model support and some of our distribution capability. And I really appreciate you sticking with me here. It is definitely still warm in here. It hasn't cooled off in the course of the last 35 minutes. So let's close and let's have some questions. Thank you.
Okay, round of applause for Scott. Thank you. Any questions?
Yes.
We have a question.
Yay.
So I was just wondering, you had a few benchmarks.
Yes.
One was Google platform, sort of CPU kind of stuff. So are you benchmarking against TPUs, or is Google still doing TPUs? I'm not really up on it, but.
Sure. No, great question. So a lot of our benchmarks to date have focused a lot on training. We have done some work with inference where we see ourselves as using TPUs as more of a, maybe a target consumer of some of the trained models that we've deployed. Today, we've been able to take models and train them on GPU for deployment on GPU or FPGA. And we've simplified the process of, we're trying to bring the big red easy button into that so that you can very rapidly target those clients wherever they sit as your inference platform. We think TPUs are very interesting. We have a couple. We're an engineering company, so we're constantly building stuff like that inside of our organization, but we're really glad to see that folks like Google are deploying it in their cloud, and that we're also starting to see a lot of folks who have traditionally made devices like DSPs and other accelerators looking at how they can be a part of the inference equation. We don't see TPUs as being particularly good for training right now. We think that they're a little bit weak because of generally the architecture that they're used within is more set up for data in, data out, and very low latency. But we're also very pragmatic in that we recognize everything changes a little bit overnight. So when we build our software, we do so in a way that makes it very modular, so we can start feathering in different capabilities today. What we see is that CPU only is a pretty awful experience when you're trying to train something new. And so today what that means for us is build the tighter coupling between the CPU and the GPU. Let the CPU handle things like data preparation and also the management of cluster resources as a whole. And then really otherwise kind of get a little bit out of the way of the GPU and get as much data shoved in there as possible so that it can run full out for as long as you need it as a training server, and then protect it with things like cloud orchestration environments so you can fence it off for when you need it as a inference platform. Did I kind of get there on the question? Okay, good.
Any other questions? Okay, thank you, Scott. Round of
All right,
applause,
thank you.
please.